Okay, so good afternoon. I will try to give a personal perception of some of the topics related to what is I understand is the topic of the event of the meeting, and as you will see by the title, is kind of a little bit even philosophical or religious type of speeches. I may be saying things that may disagree with some of what has been said before. You don't have to believe me, just, well, I'll try to raise some potential issues. So let me see how this works. So I understand this is what has been said, or what is kind of the topic of the event, is that we start writing simple codes and we end up writing complex and more complex codes because we do a lot of supposed optimizations in many cases towards a given target machine. And the end of this story is down the drain here. And this is what I think we are facing. And the message would be that really there is some hope, and there are ways of kind of recovering a little bit of relatively simple codes which are working across a relatively wide range of machines. That would be my perception or my message. And the important thing there, I think, is a lot of this problem, from my point of view, has happened because at the architectural level, what at some point in time used to be a layer which decoupled the hardware from the programming models and from programmers was pretty clean and pretty neat and very good separation. But with multicores, it started leaking, and you had to know more and more about the internals, and you started knowing and using more and more about the internals. What I think is, that's why I think we have to recover that, and the right way is, I think here it's a lost battle. There's no way of recovering that down here. So the idea, what we have been working over the time, and the ideas that we're trying to propose for a long time, is try to recover a certain level of osmotic membrane that decouples what's underneath from the applications, and providing mechanisms that let applications steer a little bit the hardware, but not really being a direct in control of every single thing. So the idea is, and this is one of the ideas which probably contradicts, I think for programmers to survive, we or they have to forget about the hardware. It's probably very strongly stated this way, but it's a little bit in that direction that I think things have to evolve, is really forget about the resources and try to focus on the logic of your application. I believe that this can be done with task-based models, and task-based models based on so it's a very small incremental change over existing classical, typical, imperative type of programming, but it's only based on a single mechanism to steer this how you convey information to the hardware about what your application is using. And this single mechanism, from my point of view, is this in-out type of annotations that specify what is used and what is produced by your computation. So it's just a task-based model with a single annotation that specifies which data is read and which data is produced. And the good thing here is that it's a single mechanism. You only say what data I use, what data I produce. But it's a mechanism that can be used for runtimes if they are smart enough, and that's a challenge for implementers of runtimes. But if they're smart enough, it's a mechanism that lets you do two things. One of them is you can do extract concurrency, extract parallelism, in the same way, and that's where the name of our approach, the sub-SS OMS, is the incarnation of our implementation today, but the SS comes from superscalar. The idea comes from superscalar processors that can execute out of order all things that otherwise is a sequential single ISA sequential programming. So this knowledge of what is read and written lets you identify potential concurrency. because it's based on the data that you access, it has the potential of letting the runtime optimize things like localities and data accesses. And that's why I think it's a very, very powerful, very, very useful mechanism. We have been working on these kind of things, trying to push for that, trying to preach for that. We were somewhat successful in promoting some of these ideas to OpenMP over the past time. Probably it's not that many people who has written these task-based programs in OpenMP. I still insist and still personally believe that's the right way to go. So, nevertheless, if you have a very good programming model, assuming OpenMP was, or assuming OMS and a little bit what has been said before, I mean, really it's not that important, the exact precise programming model. And having a task-based model is okay. The consideration I wanted to make is that even if you have a proper programming model, does not guarantees proper programs. Typically they will have a lot of flexibility which can be used wrong, and it's difficult to recover or to undo or to the features of legacy codes, and not only of legacy codes. The thing is, legacy minds is that we have been educated or grown with a certain type of mentality, which I think is what has to change. Okay, and we have to change from a latency-oriented mind to a throughput-oriented mind, a mind where we don't care that much about which specific hardware does what. Forget about the resources. That would be my perception, and work more in a top-down methodology where you just specify hierarchically from top to down all the potentials of concurrency. Just try not to stall. Try to instantiate as much work as you can without stalling. Is a way of thinking of the potentials of concurrency. We are used to a bottom up where we are in control of everything, and I think we have to move to a direction of thinking globally of potentials. And that's good, but specifying only local characteristics. And the magic would be that the system should be able to execute these things. In reality, we kind of present that as something for going to exascale, but in reality it's not true. This is for exascale and before. What I'm trying to say is this is general for parallel programming in general right now, even on our current machines. And I believe it is disruptive. It is what we propose continues being C, C++, Fortran with the pragmas. It was mentioned before, things that don't look that disruptive. And my perception is they may not look, they are. The importance of revolutions is the change in mindsets between before the revolution and after the revolution. And from my point of view, I think this is a change in mindset which is really disruptive. So in trying to educate or trying to promote these things, I would like to do the first advertisement type of thing. Is we have one in the POP project, we are doing this kind of analysis and the first thing is trying to understand the application. And I will, although this could probably be the end of my presentation, I think I'm going to take the next also 20 minutes to go into more details. But the analysis, understanding, and this has been said before by many people, really understanding what's done by our applications, and understanding the fundamentals of the applications and of the systems. So we are talking about, there's no need of talking about catch, this catch size, this associativity, this block size, or this. We need to look at the concepts of locality, what locality means, okay? So what I'm trying to say is that we're trying to do detailed analysis, very detailed analysis, and characterizing abstract global characteristics of the applications, which kind of can be used in a steering parallelization effort in the right direction, okay? And we do the analysis and we do the in cases people wants to see how we try to apply, or we can apply the above ideas about the task-based models, we can help people doing that. So these people can apply here for getting those analyses, and I will be showing examples now. So my idea now is to give some examples, some recommendations, some feelings that, from my point of view, are good practices that I would like to see more and more, and this is what we'll try to promote. I would like to see some of these things more and more used. And I have pointed them here as an index, and I will go through them, okay? I will go with a couple of slides through those, and try to explain a little what they represent. From my point of view is that there is a lot, and I agree that I mean, and I was saying different. At the end, HPC parallelism is nothing. We are selling. You never get millionaire by buying something that costs 10 times because you buy 10 cores and you get a benefit of 10. The way of getting millionaire is buying something that costs you 10 and getting a benefit of 100 or 1,000. That's the way of getting millionaire. So parallelism, we are doing this proportional increase. So the benefit has to be on how we really get benefit from that faster execution rather than the faster execution itself. Anyhow, doing that by full total rewriting of applications, I think is expensive, it's difficult for many people, and we are aiming or looking at ways of doing that in some sort of incremental, in an incremental way. So let me go through some of these recommendations and see, for example, the first one is about symptoms. And when you go to the doctor, you should be, if you have a cold, you should not take the antibiotic and then go to the doctor. You should first go to the doctor, and if he tells you this or this other antibiotic, that's what you should take. And it has been mentioned, we should really understand the real detailed microscopic causes of program behavior, both things, macroscopic and microscopic, and probably this is one of the things that we do in POP. So the first thing is that it's a way of presenting behavior of applications in a macroscopic number, just 6 numbers. You look at these 6 numbers down here, this gives you kind of an assessment, a synthesis of what is fundamental in your application, the fundamental kind of bottlenecks. It's not on this syntax routine, it's not about this other. They are fundamental things. It's a language that is valid for a chemist, is valid for a doctor, medical doctor, is valid for any application on any different areas. So it's a language across many different fields. So that's why also POP is kind of transversal to any specific area. These numbers, and I think this is one of the achievements of getting to a common language of presenting performance and discussing about it in abstract terms. Of course, reality is that these numbers derive and come from many, many different causes underneath, underlying causes. Some of them, and this is another thing which is an important thing, we have mental models of how machines behave. And the reality is that machines behave in very, very often in very, very, very strange ways. I mean, I was discussing with John McAlpin at Supercomputing about horror stories about how an Intel Core was behaving. Okay, so these things happen and will happen more and more. So we need this abstract description that I was mentioning at high level, and we need detailed microscopic understanding of what's going on, detailed statistics, and trying to understand the real underlying causes. Very often, when we got methodologies that just look at integrals of things, the total time taken by something, I mean, we are not looking at the microscopic, and unlike in life, and why does people do material simulations? Is because the macroscopic behavior of the thing depends on the microscopic structure. So we need to present the macroscopic information about the behavior, and we need to dig down into the microscopic reasons for that behavior. So this is something very important that we try to do on applications of many different areas, try to understand what are the really underlying kind of characteristics. It's a little bit like many illnesses that you don't need to see the tumor very often to see that there's a marker that says there is a problem here. So you can do these studies even at the scales of today to understand and see the behaviors, what will happen at the scales of tomorrow. So just this is a very important thing. And my message would be, it is important to try and do this understanding of the behavior of the system as they are today, even trying to do something like going back, trying to not what we have been doing in the past with many of these modifications is essentially very often, I believe, is masking our symptoms. We are trying to do some modifications that we thought were good for a given machine. And yes, we maybe gained 10%, but we didn't realize the potential was to gain 20 or 50%. We didn't realize, and that starts masking the behaviors afterwards, okay? So these kind of things would be, I think, a nice thing. So this was one of my first recommendations or things I think are important to do. The second one is taskifying computation. Being able to execute taskify with dependencies, so get rid of the fork join type of mechanisms that we are used, and be able to execute things in much higher out of order executions. And one of the important things here is fighting Anders' law, which is a very bad message for all of you or for all of us who have MPI codes and want to do threading, which is we have to do threading again on 99.9% of our codes. And the task-based approaches give us the opportunity to really be lazy and not parallelize certain routines and just embed them in the previous computations or later computations without having to parallelize everything. So this out-of-order execution of tasks, of computations, I believe it's extremely interesting, extremely important. Not only of computations, it's also of communications. I believe we have a lot of people have spent a lot of time about doing non-blocking MPI calls and reordering the order of messages. Lots of these things, my belief is lots of these things could be done automatically by the reordering, by taskifying these communications with a standard OpenMP type of task-based directives. And the runtime can achieve those things automatically. We have done examples, as I show here. We have this example here. I have, sorry, there's an image. I have this other example from a Japanese mini app where we got, so you see the interesting thing. So it was only a matter of, they had already been doing iSense and iReceives and trying to do that by hand. So we just taskified this one call here of the gems, one call of these things, specified properly the inputs and outputs. By the way, I still don't understand what the application does. I still don't know what it does. But we got different behaviors, very important different behaviors, not in parts which are limited by other things. But for example, the previous information, the previous feedback was use 2 or 3 or 4 threads because more threads are going to be very bad per process. After this taskification, more threads per process are actually even better than any other alternative. So what I'm trying to say is that this top-down approach of not going to paralyze the inner level but paralyzing the outer level, not masking the systems, trying even to get rid of this effort that I know a lot of people has done, but when you do this non-blocking MPI communication codes, you are making scheduling decisions yourself. You try to make them, put them in different places, but you are making them. And they may be good in one machine, but not in other. They may be good with one data set, but not with another. They may be, so the runtime should be able to handle these things, I believe. That's an important message. I don't know how many people would agree, probably not, because one of the difficulties is feeling of being in control is a good feeling. My message is very often this feeling that we have does not match reality, and there are other orders of execution of things that are better than what we believe can be. So I would like to encourage people to taskify computation, taskify communication, because actually taskifying both things is not only that you can execute things out of order, computations out of order between themselves, or you can execute computations and communications overlapped. is that you really end up executing communications out of order between themselves. And in reality, if you think of it, MPI is a pretty sequential programming language. Okay, there's a lot of inner state, there's a lot of matching semantics. All of these things introduce a lot of, in reality, serial kind of behavior. So that's another type of message. Next one is about nesting. And nesting, probably many of you has had, or if you have tried it, a lot of people has had very bad experiences. I think it's extremely, extremely important and useful. And one of the experiences I will show you is these were traces that we had with our analysis tool from the program of Oak Ridge. Okay, this code from Oak Ridge, they had different versions of nested code behavior. It was horrible. Okay, so nesting of parallels as they are up to the in OpenMP is probably not a good idea. In this case, the transformation that we did just mostly just only taskifying. Taskifying was one, we got huge impressive speedups for this code with them, okay? But still, you have tasks like this, which are very big tasks and very small tasks. You can apply nesting and parallelize the large ones and not the small ones internally. These kind of things, I believe, are extremely important. So let me go hinting, even for the same case. I don't know how much of you use priorities in this, or if you task with priorities. Just this membrane, just giving priorities to the runtime, steering it to say this is important, this is not that urgent, is a very nice way of getting 10, 15, 20% improvements in many cases, which is an important achievement. Another message that I would like to give is about heterogeneity. And heterogeneity is good from the point of view that you may have optimized kind of hardware. It's a bad thing if you look at how to use it. So we have to come with ways of homogenizing the heterogeneity, how the programmer sees what actually is heterogeneity as if it was homogeneous. And from my point of view, this goes to the innermost level, concentrating the heterogeneity in the innermost level of this task-based kind of model, but still orchestrating the whole computation by the outer level kind of task-based approaches. And well, we have been doing things like experimenting with still sequential codes which run on FPGAs, which run on GPUs, or on big little type of cores. It's just a matter of how the scheduler optimizes it. And the last suggestion I will comment is about malleability. We shouldn't think of threads. We shouldn't think of the resources. We should think of tasks, and this process has this many tasks to execute. If there are 3 threads, it will execute at speed 3. If there are 5, it will execute at speed 5. And the thing is then that an intelligent runtime can shift resources between MPI processes and can automatically achieve load balancing, which essentially reduces the typical load imbalance effects at the end are totally or very significantly reduced. This, I think, is a very, very important type of technology. And then the final part of the comments is, we have done this at the OpenMP level, but this is and has to be done at all levels. And by all levels means we have done it as the OpenMP, this kind of granularities and memory space. But in reality, this is what we call stars because the ideas come from the superscalar processors. But in reality, you can apply it at coarser granularities, and we have a Python same thing that does the same thing. You annotate Python functions with task decorators, and they end up executing in a distributed system. And the other side is on the vector size, and we have seen the ARM SV, this trend towards larger vector instructions. At the very end, I think it's something that matches very well with the model that I've been presenting. So this is the discussion about the Python stuff, where a single Python program with task declaration annotations runs in parallel on a distributed system. And this is on the other side of the spectrum, what we are doing in terms of vector and long vectors in the RISC-V in the EPI project. We have these web pages where we have a compiler that already generates RISC-V vector ISA instructions. There is an emulator, so you can see the code that the compiler generates. There is an emulator that can show you which are the instructions that are being executed. And in reality, In the emulator, we also have timing models, and you end up seeing things like what is the program counter, things like what is the memory address part of the space that is touched, how expensive in terms of cycles on a given hypothetical target implementation that is. So we are looking at these kind of things. So my final comment is, well, is when you get to a given age, your arguments are, let's say, age before beauty, okay, before strength or before force or before. So my point is that there are some of these ideas which I think we should take them before many of those, and probably in many cases, this is the dominating current practice. My only statement is it would be important to think more on these terms. And it's a matter it's something for vendors to do their machines, but it's more a matter for programmers, for changing our mindsets and being more worried about order and less worried about overheads, for example. Being more worried about flexibility than about matching our mental model of a given architecture. So, having said that, just would like to encourage all of you, if you are interested in having an external view of your application. I know nothing about your field, the fields of application, nothing, zero. So we can just give an external view of what we believe happens. If that external view on the performance analysis is useful for you, you will decide what is more convenient. But it's kind of getting an external view is probably sometimes useful. Okay.
Thank you very much.
Thank you.
Questions for Rhesus?
Thank you for this overview, Jesus. You say use a task-based model, of which there are many, and leave the rest to the runtime. But the runtime somehow needs to understand the data flow. And is it really true that you can optimize everything automatically? Or take, for example, what Thorsten Höfler has been showing with the Gordon Bell Prize that they won this year, that you have a task-based model, but you have two humans, a performance engineer and the application developer sit together and looking at these graphs rather than having an automatic runtime.
No, I think that the graphs, so what I try to say is that hinting. So one thing is the way how you build the graph, and I would disagree that any task-based, I don't think any task-based model is very much the same from the productivity point of view, but that would be one discussion. The second thing is, if you look at the task graph, a human look at the graph, seeing general characteristics, may find out things like hints or things like...
I agree with that. I think there you agree.
Yes. Yeah. So we're in sync. Okay. So when you say, is it 100% only totally automatic parallelization? So what if it is 80% automatic parallelization? Okay. So that would be a kind of very objective. But if we don't aim at forgetting about this possible later optimization that by us looking at the graph can find, if we think of how we structure of application in an abstract way, I think we will gain a lot.
Just a short comment. So don't be shy, go to POP. And after going to POP, you also can go to the HLST, the high-level support team, who could help you to implement what you have learned with POP.
You're right. I think so. And the idea of POP is only to identify and find out things. POP is not, has no throughput enough to do the detailed implementations of all the. Our intention is try to show the way of how things might be done, and whether that way is really perceived as appropriate by a customer is is also very subjective and depends on many, many things. But there is, of course, plenty of space, and HLSTs are probably very good place to help that. Yes, I'm okay.
Thank you, Jesus, for your presentation. I have a risky and respectful question because it's about a philosophical approach, so don't be too severe. You talk about MPI as a maybe not a good model for this because it is too much serial, but on the other hand, it also introduces a way of addressing data locality. And as data locality is a key element for energy efficiency, as computing is very light in terms of computing, so how do you mix in your scheme of optimization the way of keeping data in place, waiting for treatment? And MPI seems to me a good way for doing so.
No. MPI, actually, when you program MPI, it helps you localize a lot of the things. I agree with that. But it is, which does not disagree with what I said, that it has many things which are very, very serial. What I was trying to say is that, and this thing of locality has nothing to do whether I use blocking or non-blocking communications or where I try. This is what I was trying to say, that try not to use the ordering things of MPI, right? And so the locality, MPI is there, MPI will be there, I'm not saying against it, but is that the ordering thing, I think, should be left to the OpenMP side. Then OpenMP locality, for example, you have all the things with places and all these kind of things. For example, my personal perception is that that's not a good way of dealing with locality. My personal perception is a good way of dealing with locality is I have in my task, I know what are the inputs and what are the outputs. If this task produces this data and this task reads that data, the system should be able to know that this task should be scheduled close to that one. These kind of things, there's a very, very, very easy and very simple way of using that, we have been doing work on this thing. I mean, we have implementations where the runtime has internal tables of where all the data is, okay? And you decide, we have done these things, whether these things get into commercial implementations, maybe not, but these things we have done, and they are very, 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 very interesting, very powerful. But there is one simple thing which is extremely simple, and is this thing of I have a task which produces one data, schedule the task which uses that data immediately. This change of order of execution of tasks will give you huge amounts of locality under conditions where you can probably not even, because there may be conditionals, you cannot do that by hand, and you can do that automatically.
My question is related to the scalability of your task approach. And so what is the level of number of tasks you have already deal with? And what do you think about this problem of scalability?
So I think probably the number of tasks is not that big of a problem. We typically have implementations with task graphs in the order of 8 to 10,000 tasks, right? So you see the future. The point of and there is a point there, which is the overhead that we have. And our personal, in our BS implementations, the overheads are, in some cases, very, very large. And is this point here. So order and overhead, what do you think is more important? In my case, if tasks have granularities of the order of half a millisecond, it doesn't really matter how many tasks you have. The overhead of this runtime is going to be an epsilon compared to that. And taking decisions very, 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 very fast. So arguing that my MPI implementation has 1 microsecond or half a microsecond latency, or my OpenMP runtime has half a microsecond. I think taking decisions very, 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 very fast, if the decisions are wrong, is a bad choice, because then you are scheduling a task that will take you a few milliseconds probably. So the thing is more on the order than on the overhead. Having said so, certainly overheads are important. In our case, the overheads are in our implementations, but that's because of this philosophical thing. I don't push the people to do extremely important optimizations. It's probably very often is more a matter of using the other things and ideas that I used can give you much more than the overheads. But if you do, or a vendor does an implementation which really is very, very, very efficient tries to support this very efficiently, that's certainly great. So if your number is number of
There
tasks,
is-
doesn't matter granularity. I target the order of let's say from 200 microseconds onwards.
This is the last question for a short answer.
Short question also. A quick question. So, if I understood correctly, you're assuming that the starting point is a task-based program, whether described as OpenMP task or another programming task-based program. But do you have any recommendation on a manual process or semi-automatic process to go from legacy to a task-based program, so we can take advantage from these optimizations?
No, I don't have a suggestion there. I think the point is that the task base is something which is very incremental. A very good approach, a very, very, very good approach is take your MPI program, decide what you taskify, and maybe only 10% of your program, of your total program. And still with these dynamic load balancings, if that can let you address load imbalance issues, and you can still get 100% efficiency on your code by only parallelizing 10%. It's against standard law. Automatically, no, I don't have a suggestion.